All right. Today, as promised, we'll try to do some more TCP specifics. So far, we talked sort of generally. Let's see. Is that better? Yeah. So far, we talked kind of generally about reliable transmission. And so today, we'll try to dig into the specifics of TCP to see exactly what's going on and deal with some of the interesting corner cases that TCP has to worry about. Right, so why don't we dig right into it. I should mention first, I discovered there's something a little weird about the reference server. So if you're having difficulty one way or another, it's not clear that you need to blame yourself. I think it wasn't responding to Telnet anymore. Or when it gets a peer client, it's not responding to Telnet. Works fine on my machine, but you know. So I'm gonna fix that tonight, but yeah.
Yeah, I found when I added a peer, it started responding after like 2 or 3 minutes to Telnet. There was like a waiting period.
Okay, yeah, it's being stingy. I don't know what's up there. Hopefully, it has nothing to do with the network, and it's just some bug on in the code. But yeah, I'll have to play with it a little more. I only tested it on my machine, and then I ran it on the server. It seemed fine, but then I guess not. Anyway, for grading, we are unlikely to use the reference server, just because it makes things more complicated. But it would be nice for all of us to be able to kind of have a joint chat session between a whole bunch of different server implementations. So I want to get that going properly. Did anyone get a chat going through the reference server? Yeah.
So you're saying the reference server most likely will not be used in grading. So as long as it's working with like other machinery.
I think we will check compatibility with a reference server, like with a reference implementation for something. We'll probably run it on a local machine. It won't be that specific one. But most of the grading points will be just working within your own implementation. Right. Did anyone actually get a joint chat session working between each other? Yeah?
I did, but then the reference server sent me a bunch of invalid messages. I thought that was kind of weird.
Well, it might be forwarding something from someone else.
Maybe.
Anyone else got something running? Yeah?
I mean, not like a joint chat session.
Not a joint session. Right. That's the one I'm most interested in.
Not this morning.
Okay. All right. So let's dig into TCP then. I think there was a nice picture for the TCP on Wikipedia. We'll do that first. So actually, let's draw a picture on my own first. So the point here with TCP is to provide a reliable service to an application. So we have we stack them up like this. At the application layer, we have some program, say a web client, and make it a little smaller. Web server. And then there's this socket interface. So here we're in user space. For those of you who have taken operating systems, user space is where all programs run, except for the kernel. Programs can't look at other programs' memory and so on. It's just their own little isolated sandbox. And then below this, we have the kernel, or a supervisor. And this is where TCP is implemented. TCP is pretty much the same on both sides. And under TCP, we have the IP, Internet Protocol implementation. Now we're talking about basically function calls here, right? From the browser, there's a system call, which goes through this user kernel barrier. But other than that, these are basically just system calls. So the browser says write, So, right, I want to send a request to a server. I've made this connection. I say write to send something out, and that write could be just like you're writing to any file descriptor. So you can say, okay, send this megabyte, right? And here's a pointer to it. Right? This is how long it is. And then it's up to the kernel, in this case TCP, to deliver that megabyte of data over to the other side. To do that, it sends or it makes function calls to other parts of the kernel, which says, okay, send packet, right? So from TCP's perspective, it's getting a write request. With an arbitrary size, there's just some character buffer coming in. And then TCP needs to chop that up into many pieces and deliver one at a time with correctly formatted headers and all of that to the IP layer in the kernel. And by layer, I just mean probably a file or two, or in case of Linux, maybe 50, that provide this interface like send packets. Right? So here we're able to send individual packets. The IP layer, and these are individual IP packets, so it has a destination in it, like an internet destination. And then the IP layer sends something using the MAC layer, which sends to the next host. All right, so both on the server and on the client, we have this entire stack of things. So you would call this application, transport, network, and link layer. Right? And then under this is, we've seen this stack before, but here's the physical layer, which basically sends, that's the network interface, which basically makes some sort of physical phenomenon, sounds or radio waves or blinking lights or whatnot. And this is what actually goes through a medium. Actually, let me do it a little different than that. Right, some medium. And then usually it goes like this. So somewhere in between is one or more hosts that talk all of this. Right, so there's something in between here, usually a switch or a router. It receives these physical signals, it decodes it into a MAC layer frame saying, oh, it's for me. It has the right Ethernet address on it. It's for me. So it's received and not rejected by the kernel on this side, or whatever program is running on that side. It passed up to an IP layer. In this case, it's probably a router. So it'll see, okay, it's destined. This packet is not destined for me. It's destined for this other destination. But I know what the next hop is. Right? I know where to send it next. So it'll then send it back to the MAC layer with a new destination MAC address for the next hop. And it goes down and it's transferred on. So in this case, it's a single hop or a two hop route to the web server, but there could potentially be very many along this side. So we have implementations of IP everywhere. Every node on the internet pretty much has to speak IP, but TCP is only on the endpoints. It's rare, or somewhat rare, but certainly not that uncommon that you have TCP implementations or partial TCP implementations in the middle, and that would be usually in the form of a firewall. Okay, so the job of TCP then. We want to take a packet, take a write request, somehow get it over the internet, and then on the other end, there ought to be a matching read request from a server, and we want to deliver bytes from this write request on one end to the read on the other end and make it reliable so that you get all those bytes. You get them in the order that they were supposed to be written out, and no weirdness, like, oh, if an application quits on one end, the program crashes on one end, we want the program on the other end to somehow get aware of this, right? It shouldn't just be stuck forever. If you lose some packets, of course, we want them to be redelivered and so on. Okay, so the TCP lives all in the kernel, and the kernel is in charge of all the retransmissions and all this. The application doesn't see any of that, generally speaking. And then, of course, it also has the job of deciding, which browser window should I be delivering? No, that's on the way back, let's say. It would have to know, like, which browser window is this download going to, and that's what the port is for. Right, so if we look at the specifics of TCP, one important part is like, what is it that we're actually sending? And it's much like this peer-to-peer server thing that we're doing now. We're sending something that looks like a struct, right? A struct with some parameters in it, and then we're sending a payload of the data that the application actually wanted to send. So the internet usually allows 1500 byte packets, right? So you can have, actually I should put it here somewhere. Right, so including the whatever headers IP wants, the headers for TCP, the whole thing can be at most 1500 bytes long. That's sort of historical. The reason is that the most common MAC layer was Ethernet, and Ethernet had that as a fixed segment, fixed frame length. So kind of have to live with that. Because if there's an Ethernet anywhere along the way, an Ethernet link, and you send a packet that's too long, well, it's not going to fit. So then you have problems. It could either drop the packet, or it could split it into multiple pieces. In any case, there's issues. All right, so we're sending a long transmission, much longer than 1500 bytes. TCP will split that into writes into multiple segments. For each segment, we attach a little header on top saying like something about this segment, and then we pass it down to IP for further processing. All right, let's see what we tack on. So this is a TCP header. Byte 0 starts out like this, and then after 20 bytes, so at offset 20 starts the payload. I'm not exactly sure what they mean by this. But after 20 bytes of TCP header, then starts the actual data that's in this segment. So now we know that there was 1500 for starters. So there can be at most 1480 bytes of payload data. In fact, there's also the IP header, which is something similar. In the end, you end up with 1460 bytes, I think, is the maximum amount of data that can go in one of these packets. All right, so we're specifying a source port, right? Usually, that would be a randomly chosen number between 32,000, 65,000, but it's not necessary. It can be whatever you want. When you're establishing a new connection, right? The origin port doesn't matter. But at least if you would like, you can specify any port you want there. And of course, when the web server is sending a response back, it's coming from port 80. We connected to port 80 on the web server. For responses, everything will be, the source port will be port 80 in the case of a web server. So we have a destination port and a source port. Right? This uniquely identifies for a unique pair of hosts. The source port and destination port uniquely identifies a TCP session. Right. The entire quad, what did we call it? Forgot the name again for a quartet. Yeah, the entire quartet of the source IP, port IP, source port, destination IP, and destination port. That's a unique identifier for a session at the current time. But it's not quite unique for, say, things that happened in the past. And we'll see that in a little bit. You could imagine, like, I established something from port 80 to port 80, just to take a silly example, between these two hosts of mine. And then I shut down the connection, and then I can open a new connection, again from port 80 to port 80. And so now we have two different sessions which have the same identifier, but they shouldn't be happening at the same time at least. And that's something we actually have to worry about a little bit. We'll see that later on in practice. All right, and then we have this sequence number. It's a large number. This is, in TCP, it's the number of bytes that we've sent. Right. So this is before the beginning, before this transmission. The byte that is, I guess it's the index of the first byte that's coming. Right. So if I haven't sent anything yet, it'll be a 0. Except we start with a random offset. So when you first start this up, and we'll see a little bit later why, we actually pick a random number to start with. So when you first set up a connection, we pick a random number in the 32-bit range, and then from there on, it's the number of bytes that we've transmitted. And the acknowledgement is the same thing, but here we're saying, what is the next byte that I expect to receive from you? Right? So I received 1,000 bytes, and I'll say, okay, next I expect 1,001. That's what we're getting back from the recipient. Okay, and then we're saying a few other things, and some of this isn't quite, this has been around since sometime in the 70s. When is it? 74. A lot happened around then, like Unix and C and TCP and lots of good stuff. Anyway, so here we're saying, where does the data start in this big packet? Right? The length we don't have to worry about because that's part of the IP header. I'll see that a little later on. And then we have a few flags. You recognize some of them. SYN, all right? I'm trying to start a new connection. It's a very special sort of situation. And then we have ACK. This basically means the acknowledgement number means something, right? So in the first packet, at least, when you send a SYN packet, there's nothing to acknowledge. So we have to basically say, okay, I'm not acknowledging anything right now. And just putting a 0 would mean I'm acknowledging the next packet after 2 to the power of 32 minus 1, right? That's why. Fin means we're ending this connection. It's almost symmetric to the SYN. And the rest of them don't mean much. Let's see. This RST is very useful for special cases. We'll see in a bit. Push means nothing. It's not something we use anymore. Urgent means nothing. Let's see. ECE, is this early congestion? Let's see. Oh, here it is. Right. Okay. So I think we can ignore that one for now. There's ways of sort of adjusting to congestion without having to see a lost packet, and that's what this is used for. And NS, what's that? Okay, that's something relatively new. Nonce. Okay, we can ignore that too. And then the window size says nothing about congestion really. It says on the server side, how many bytes can I actually receive? So it could be something like a buffer size, right? I am ready to receive 300 bytes and that's it. So then there's no point, even if the network has lots of capacity, I really shouldn't be sending more than 300 bytes until the server tells me they're ready for more. This seems a little silly, right? It's so easy to allocate more memory, let's just do that. But the point is, some of these servers, they're not these big honking servers in data centers, they might be a light bulb in the ceiling, and they don't really have that much memory. They shouldn't be using much memory. And so they can advertise a small window size, and everything will work for them as well. Of course, there weren't any light bulbs speaking TCP back then, but then all the machines had less capacity instead. Maybe they were similar to a light bulb to some extent. So 74 after all. Okay, and then there's a checksum. This is not much of a checksum, unfortunately. It's you add up all the bytes in the packet, the payload, the header, many of the header values. Just add them all up, and that's the checksum. Unfortunately, it's not a very strong checksum. It could have been designed better, but it's a long time ago, and it's really hard to change these things because you have maybe a billion devices speaking TCP. With this checksum implementation, if you go and change it, they will reject all your packets. So we're stuck with that. Nobody uses the urgent pointer. The intent of the urgent pointer was in a telnet session, let's say. You might have typed in a lot of things, and it's the other end isn't receiving them yet. Like maybe the server is on the server side, the program is not calling read. It's just not happening. There's some buggy program, let's say, and you want to kill it. So how do you kill a remote program if it's not reading the console? Right? Control C isn't going to work anymore. So that was the point here with the urgent pointer. If urge is set, then you can sort of deliver this byte out of band. It's not in the order of all the other transmissions. So you could get your Control C delivered to the telnet or SSH server, so it can kill that other application that's running. That was the idea. It's not something that anybody uses. It was really hard to get it right, apparently, and so it's just kind of a leftover. Fortunately, it's only 8 bytes per 16 bytes per packet that ever was sent with TCP. It's a lot of bytes, but people make mistakes. Okay, so this looks like a struct, right? Here we have 16 bytes, another 16 bytes, 32 bytes, and so on. That's exactly what's sent over the network. Maybe we should look at the IP header just to see how it all adds up. The IPv4 header. Good. All right, so here's another one. So when you're sending your packet, you're sending first this. That's 20 bytes. And it starts at 16 here and it goes up to 20. So we have 20 bytes of IP header, basically saying where does it want to go, where is it coming from, and some other things which we'll worry about later. And then comes the TCP part that says which application is it coming from, which application is it going to, essentially, or maybe which socket, file descriptor, and something about the ordering of all these packets. And then, of course, an Ethernet frame. It's the most common MAC layer, linked layer. So in addition to our 20 bytes of Ethernet, of TCP, 20 bytes of IP, we also have it looks a little different, but I wish they would look the same. How do we add these up? 8 bytes, another 16 bytes. Is it? Can't really tell how many. And here's the payload, and then there's another checksum on this one. How many bytes is this? 8? 20. So it's optional. 22. Okay, 22 to 26 bytes of Ethernet frame. So we go. If you just read the whole thing that's coming in over the wireless link, right? We have 20 bytes or so of Ethernet header saying who's the next receiver of this thing, and then 20 bytes of IP thing that says, oh, who's the eventual end host that's receiving this packet, and then 20 bytes of TCP thing that says which is the application that wants this stuff, and then comes the data, and then at the very end of it comes a little bit more. This one here that says, oh, what should this entire thing look like on this one hop? All right. The CRC checksum is a good checksum, and if it checks out, that means none of the bits changed along the way from one hop to the next hop, and so we can keep this packet. Otherwise, we have to throw it out. All right, so let's take a look at TCP specification. We've looked at RFCs a little bit before. The RFC being a request for comment. It's a little archaic. It looks like it's like typewriter font and it's paginated and so on. But I think it's still the reference source for everything, and RFCs are still coming out for new standards to some extent. So we may as well use it. It's kind of nicely done. So a standard connection request looks something like this. Try to make it a little bigger. So here we have two of these connection endpoints, TCP-A, TCP-B, server client, let's say. The server is currently in the state listen, right? It's waiting for incoming requests. TCP-A sends a sequence number and a flag set to SYN. So this is one packet here that we're sending. So that one flag is set to SYN, and then we don't care what's in the acknowledgement part of the header. And in the sequence number, we put a random number and send it off. Okay. And so on the TCP side, on the TCP-B side, server side, it changes state. It says, okay, I'm ready. I have received an incoming connection request. So what do we do then? We acknowledge the fact that we got a connection, and we say, oh, and by the way, I want to establish a connection the other way too. So you can actually have a halfway TCP connection. I don't think I've seen an example of that in use. We should try that sometime. Okay, so we're sending back some other random sequence number, right? Two random sequence numbers, and then we say, oh, yeah, and the next one I expect from you is byte 101. So now we say SYN because I'm establishing my direction of the TCP connection, or that is, I'm establishing a new sequence number, right? This is the one we'll use to order everything in my direction. And then ACK, because my acknowledgement actually means something. I've received your first SYN. And then finally, and this one is kind of optional, the application, the client then says, okay, here's well, we have to give it a new sequence number, because if we stick with the sequence number 100, then the server would have to throw it out as a duplicate. So we give it a new number. This is 101, even though there isn't a byte of data in here. We kind of count the ACK as a byte, just so we get a unique sequence number. We're saying, okay, I got your 301, and this is just to acknowledge that. So we're not establishing anything more. We're just saying, okay, I'm going to expect from you next byte 301. So everything's byte by byte. And then now I can start sending data. And in fact, you can do this. You don't need this one. You can just do this one directly. So we piggyback, it's called, the acknowledgement with the data. Really, there's no extra cost to this. There's always an acknowledgement in every packet. And so if I want to start sending my request, we can do it now. Okay, so that's your expected behavior, sort of what you would usually see. You can also, strangely enough, you can just, nobody has to be in listen mode. if we have agreement, right? If we've said, okay, I'm going to use port 80, you're going to use port 81. Now we can just both say, okay, let's go. And we start a connection in either direction. TCP doesn't care. So now I'm acknowledging, I'm synchronizing my end, right? I'm sending a request in my end. TCP/B is sending a request in its direction. So this all looks the same except for there's no acknowledgements yet. Now we can just acknowledge in each direction, and we're good to go. This is very rare. I've seen it in some peer-to-peer applications with firewalls in the way. Usually speaking, this pre-coordination of when we're going to connect and which ports we're going to use, if you already have that, then what's the point? And why would we do this? I guess it can be handy if you don't want to have a port open. You don't want to be receiving connections from just anyone. You want to kind of keep it a little secretive one way or another. Okay, so one of the things we have to deal with here is the network isn't all that reliable. Right? On the one hand, you might lose packets, but on the other hand, you might also get duplicate packets. Any idea? How could you end up with copies of packets? Why would the network do that? That's really stupid. Yeah?
If the sender thinks that the packet was lost, it'll resend it and you can get both of them?
Yeah, certainly. That would be, so now we're talking about the sender, the sort of end-to-end senders. And that, I guess that's part of the protocol. Like TCP would be aware that it has sent another packet. So in that sense, it's not the network screwing up, it's the endpoints in charge of this retransmission. But something similar can happen along the way. So if we have a wireless link and we don't get the acknowledgement, like for a wireless link, you send the packet and you get an acknowledgement back for that link just to have some reliability. The receiver might have gotten the packet anyway. And then later on we retransmit, and the receiver isn't going to remember every packet it's ever seen. And remember, it's not supposed to look at the TCP layer, so it doesn't know about sequence numbers. It just sees another packet and it'll transmit it. So that's that's one way you can get duplicates. So you could, in principle, then end up with duplicate SYN packets in the network. Right? So you establish one connection, and then you're done with it, and then later on comes another SYN packet from the same connection with the same SYN. And what do we do about that? Right? So here's an example where, oh, that's not an example. Here's an example, kind of nice. I send a SYN packet, but then, so this is, I'm starting up a new connection. But we've had some activity earlier on. So it so happens that a duplicate packet shows up before me. Right? I started to make this connection, but we had this connection before. You know, this is common with a web browser. You make lots and lots of connections to the same web server all over the time. You all the time. You get this picture and you close the connection. You get another picture, so on. So we have all these very short-lived TCP connections that tear down, and we start another one to the same destination server. Of course, since we pick a random source port, usually it would look unique, right? It would say, okay, I haven't seen this connection before. I haven't seen this port pair before, so we'll just treat this separately. But sometimes you get unlucky. There's only a 16-bit port number. So it's one chance out of 65,536 that you pick the same port number as before. So in that case, what do we do? So here the server received the SYN, which the client isn't aware of. right? This is just kind of delivered. We have duplicate delivered by mistake. Server receives the SYN and says, okay, fine. I'll acknowledge it and send back a request. Send back my own SYN sequence number. But on the client side, we know that we are establishing a new connection with sequence number 100. Right? And we're expecting to get back an acknowledgement for 101. Instead, we're getting back an acknowledgement for 91. Okay? So in that case, we have to tell the other party that there's something wrong here, right? It's better to tell them early and try to kind of fail this out than to try to recover somehow. So we see, okay, you're acknowledging the wrong thing. This doesn't make any sense. It's before the sequence number that I even, it's even before the first one I ever sent. So I'll send a reset back. This is that little flag. You set this flag, reset, then the other endpoint will tear down the connection and just forget about it. It can get worse than this. There's a couple other nice examples here. Yeah, so here we have an ongoing TCP connection, right? The client has connected to the server, we started a download, and suddenly the client crashes. A crash here is worse than just the web browser crashing. A web browser crashing, we can live with that because, as you see in here, TCP is all handled by the kernel, so the kernel will know, oh, that application is gone. Let me just send RST packets or FIN packets for all of the established sessions, and we're good. But what if the entire machine crashes, right? So now the entire kernel state is gone too. We come back up, and the user is upset because they had a crashed machine, but now they want to talk to this web server again. But it doesn't work because the web server thinks we have an established connection, and I'm trying to establish a new connection. Right? So again, we're relying on, or not relying on, but this is under the condition where the source port, which we picked randomly out of 65,000, is the same as last time, just by accident. So in that case, we're trying to establish a new connection on the same session, unique session ID. The server sees, oh, you're trying to synchronize when we already have an established connection. But let's see. Yeah, so it can't just tear down the connection though. That's a little dangerous here. If you just send anything in, you could force a server to terminate the connection of someone else. If you just send a bad SYN to the server, you say, okay, I'm this guy, right? Let me try to establish a connection. I'm going to use whatever port he's using and then shut it down. Or maybe do it for every port. 65,000 packets isn't the end of the world. Then you can shut down other people's connections. So that's not what's going on. Instead, we say, okay, in fact, we already have an established connection, right? So I'll just acknowledge what we already have agreed upon. And then the client sees, oh, that's not really what I think is going on, and it then tries to tells the server like, okay, that's it. Let's shut this down. Okay, so the reason that the server can trust the reset, but not this one, is that it has the right sequence number in it. The sequence number is really hard to guess. It's out of four and some billion. So you send a reset with the correct sequence number, then the server can trust that this is coming from the right host. Okay, so we send a reset, and then it's all closed down, and we can start over and reestablish a connection. And I think there was another interesting example here too. There's a few. I think we'll move on, but I propose you take a look at this RFC. It's not all that long. Has lots of interesting examples, and we'll move on to the fin. So everything's going as normal. We have an established connection, and now we're done, right? We downloaded the whole thing, and the user program calls close on the file descriptor or shut down. Same thing. So in that case, here it's the client side that tries to close it. Well, it'll send an acknowledgement. It'll say its sequence number and acknowledgement, and then it'll say fin. Put that flag to 1, and the server knows that this is the end of it, so it'll acknowledge that it received the fin, just incremented by 1, and eventually the server program says, okay, let's close it. So this is slightly different from what you would expect with a normal file descriptor. You open a file, there's only one party to this. So you open the file and then you close the file, and that's it. In the case of a TCP connection, there's 2 parties involved. And so here we have 2 of them wanting to close it. You don't close unilaterally, I suppose. So here the server then later on says, okay, I'm going to close my end too, sends a fin, and the client acknowledges that, and then we're done. Almost. The kernel actually has to remember this for a little while. Remember that, oh yeah, we used to have this ongoing session, because there may well be some packets coming in later on that belong to this session. And those should just be discarded because this session was closed. Right? As we discussed already, you might get duplicates. You could also, if you get unlucky, you'd have quite variable delay on the transmission. So you send a lot of packets. Some of the packets go a circuitous route, and they show up a few seconds later. It's not all that uncommon. And you need to sort of be able to deal with this and know that this belongs to an established session that we already kind of finished up, and let's not worry about it. This also helps with when you try to establish a new session. You don't want to reuse one of those ports, and this is where that's SO. Is it just SO reuse? Is it? I don't remember the socket option. Anyway, the kernel typically will remember that, oh yeah, just a couple of minutes ago or 1 minute ago you used this port for a connection. Don't do it again because I'll get confused. Right? We're connecting to the same end host with the same IP. I'm using the same IP, and now you're telling me you're going to use the same source port too, right? Now we're repeating the session ID for a connection that was just finished. So there might very well be packets flying in that were late, and that's going to get a little screwy. So that's why the kernel complains, unless you tell it to not worry about it, which we did in this homework, and then we're allowed to use the same port again. No, actually, in this case, it was a listening port, slightly different. Anyway, the situation is the same if you try to connect with a particular port on the client side. Okay, so there's a 3-way handshake for finishing the connection as well, and then we can wrap it up. So a few interesting other corner cases that could happen, and I think, yeah, let's start with this one. It's called a denial of service attack. So there's a lot of weird people on the internet. Some of these weird people like to say, try to shut down a web server because it's publishing some information they don't like. And one kind of nice trick you could pull, having looked at all of this TCP stuff, is you could kind of fake a, let's see, denial of service SYN flood attack. So kind of a nice attack is you send a SYN packet from a fake IP address to some server. In fact, not a SYN packet. Right? Not that complicated. And what's really nice about this attack is that it doesn't cost you almost anything to send a SYN packet. It's about 40 bytes, right? The IP header and the TCP header. So you can send many very quickly. But what happens on the server side? The server needs to set up some state, allocate some memory for this incoming connection. Right? Remember that what is the sequence number? And what did we tell them, right? And then it sends out an acknowledgement and it doesn't hear anything back. What does it do when it doesn't hear anything? It's not like it sends a SYN ACK, right? It sends another SYN together with an acknowledgement. And when it doesn't get an ACK, what does it do? Well, it sends another SYN, right? Until it gets an ACK. So now the server gets to do a whole lot of work. We spend 40 bytes. Send 40 bytes out. The server is working for a couple of minutes here to try to establish this connection. So we send very many of those out, and the server is out of luck. Right. So a nice countermeasure to this that is in place all over the place now is the server doesn't actually. Don't establish any state on the server for a SYN packet. But now that gets tricky because we actually have to kind of remember that we acknowledged a SYN. We have an ongoing connection. We have to do something here. So we have to send a response. Send an ACK back with a SYN, a sequence number of our own. But then if we can't remember it, right, we can't afford to remember that sequence number, because then we're keeping state. So we need a tricky way of establishing or setting our own sequence number without keeping any memory on our side. And the kind of handy solution is to say rsyn is a hash of the incoming SYN and a secret. So this is a nice cryptographic hash which you can't reverse. And the secret is only known by the server. So now we send a SYN packet back, but it's not actually a random number. It really looks very random because it's based on a random incoming sequence number and our secret, and it goes through this irreversible hash. So now we sent that packet back, but we don't remember that we did it. And we don't retransmit or anything like that. We just send that SYN ACK. And then when the client's third message comes in, then it says, it has its next sequence number, SYN +1, and then it has this hash, right, which we sent of SYN plus secret in the SYN ACK packet from the client, right? In the third packet from the client, it'll say, oh yeah, and we have this ongoing connection, right? And this is, I acknowledge that you sent me this number. So now we know that they received our response, and we can check that it's the right one, right? Everything checks out. We know that we're talking to someone that actually exists on the other end without having remembered anything. We know that it's the right one because they couldn't possibly have computed this number. And now we can afford to establish a proper connection. One of many nice little tricks in the network security side of things. Okay, we're out of time. We'll talk a little bit about a few other weird things going on in TCP next time. And then we'll move on to other reliable transport, I think.